What I'm going to talk to you about tonight, the topic was to be soil testing. I can talk to you and explain how to take a soil sample in 2 minutes' time. And I thought you wanted more than that. So I decided that tonight we would do a review for most of you. I'm sure most of you know this, you've heard it before, but if you're like me, when the time comes after a meeting, I go home, and if I didn't write it down, I forget most of what I heard. If I did write it down, I forget where I put it. So what we're doing tonight, we have Mr. Adam Russell from Texas A&M at Overton. He is the Extension Communications Specialist. He's been there, what, about a year?
2 years this morning.
2 years. Time flies. Anyway, he is going to record this. And Al, I hope that Marianne can link this talk to our website so that anybody wants to see more about it, that they can look at the website, and maybe it can be put on the Overton website, overton.tamu.edu also. I got requests from HayTalk people to record this and post it somewhere where they can access it. And that goes national and international all the way down to Australia. So what we're going to talk about tonight, something about plant nutrition. We're going to review the soil as a storehouse for plant nutrients. Am I blocking you?
No.
Okay. We're also going to talk about soil acidity and plant nutrient availability. We're going to talk about limestone and liming acid soils. We'll talk a little bit about fertilizers, and then go into soil sampling and interpretation of soil test results. So here we go. Introductory plant nutrition. What do plants need to grow? And I'm going to talk primarily about the nutrients that plants need to grow. In addition to sunlight and water, they need carbon, oxygen, and hydrogen. They get those from air. They get hydrogen and oxygen from water also. And then we have the plant nutrients that come from the soil. They have to come through to the plant through the roots. The primary are macronutrients, or nitrogen, phosphorus, and potassium. Secondary nutrients are calcium, magnesium, and sulfur. And then we have what we call the micronutrients: iron, zinc, copper, manganese, boron, molybdenum, and chlorine. Plant nutrients deficient in the soil have to be applied as fertilizers, or they can be applied as manures, gypsum, limestone, whatever you have available to put that nutrient out. Now, the soil is a storehouse for plants and water, for nutrients and water. I've tried to depict the soil clay. The clay in the soil is the chemically active part of the soil. It's negative in charge, so it attracts positive ions like potassium, magnesium, and calcium. We call these positive ions cations. It had nothing to do with the cat, but cations, not cations, like I've heard somebody call it one time, C-A-T-I-O-N-S. They also have an affinity to hold phosphorus, the negative charged nutrients, nitrate and sulfur, sulfate. And then there's water between these clay particles. It's either tightly held as adsorbed water, or it's loosely held as capillary water. Plants can get the capillary water a lot easier than they can the adsorbed water. Capillary water will occur in these soils right after a rain, after the soil is drained and the soil is still holding some of that water the plants could get very easily. Plants take up potassium, magnesium, and calcium, these positive charged elements, plant nutrients as we call them, and they give off hydrogen to keep the neutrality in that soil. When the plant has given off so much hydrogen to the soil and we don't keep it limed, we get an excess of hydrogen, and hydrogen is what's measured when we determine pH, potential hydrogen, pH. So an acid soil is excess hydrogen, and when it gets sufficiently acidic, the aluminum in the soil particles itself comes out, solubilizes, and is available to the plant. And aluminum in sufficient concentrations is toxic to plant roots. It prevents them from growing and getting water. And when we look at the pH scale in chemistry, it goes from 0 to 14, but in soils it doesn't cover that range. It'll go to maybe as low as 4, sometimes very low 3, rarely, and up to 7. 7 is neutral, and above 7 is basic. It goes out to about 9, maybe 9.5 once in a while. Below 7 is acidic. Most of our soils in East Texas are acidic. Yes, sir.
You want it at 7?
No, you don't have to have it that high. If you want to grow alfalfa, you have to have it at near 7. And I wish more people would want to grow alfalfa in East Texas. I'm getting tired of being the only person growing it. Somebody else needs to take over. Anyway, acidity affects nutrient availability. In the pH range from about 6.5, maybe even 6, out to 7.5, 8, the primary and secondary nutrients are most available to plants. The micronutrients are a different story. As the pH goes up, they become less available to the plants, except for molybdenum. Molybdenum is more available at higher pH than it is in acidic soils. What causes acidity? Leaching of cations, those potassium, calcium, magnesium, basic ions, causes acidity. Uptake of these cations by plants in exchange for hydrogen ions in the soil causes acidity. Mineralization of organic matter by microorganisms forms organic acids, and oxidation of iron sulfides forms sulfuric acid. The biggest acidifier in agricultural operations is nitrification of ammonium nitrogen fertilizers. And I'll go into that a little more later. And some soils are naturally acidic, and acid rain contributes a small amount of acidity. Not much anymore since sulfur is being taken out of the stack emissions at power plants. Here's what I wanted to show you relative to nitrogen fertilizers causing acidity. If we look at anhydrous ammonia, which is 82% nitrogen, and we use very little of this in forages because it has to be knife injected into the soil, and then the slit has to be covered, or otherwise we lose the ammonia. Urea is a granular, 46% nitrogen. Ammonium nitrate is 34% nitrogen. And urea ammonium nitrate is a liquid formed by combining urea and ammonium nitrate. It comes out to be 32% nitrogen. These 4 nitrogen materials each contribute 1.8 pounds of calcium carbonate neutralizable acidity per pound of nitrogen applied. So if you apply 100 pounds of nitrogen from any one of these 4, it will take roughly 180 pounds of lime to neutralize the acidity formed. We also have ammonium sulfate, which is 21% nitrogen. It's a stronger acidifying nitrogen material than these other 4. And then we have the ammonium-containing phosphate materials, which are stronger acidifiers than these 4 nitrogen materials. Any questions on that? What are some of the effects of acidity? When the soil pH goes down below about 5.5, aluminum, I said earlier, solubilizes out of the soil, the clay, and it rises rapidly as the pH goes down. So at pH 4.5, the soluble aluminum content in that soil was around 15 parts per million, very toxic. You can see here, and I'll show you a bigger picture of that in a little bit. We also have manganese toxicity in some cases in strongly acid soils. This is down in the Gulf Coast prairie, and this is corn. In the background, this corn was limed. In the middle, it was not. And the pH was about 5.2, and that was a very high rainfall year, spring, and that soil was waterlogged. And the manganese normally in the soil is a manganese oxide. When the soil gets waterlogged, the bacteria can't get oxygen from the air, so they start stealing it. So they take it from manganese oxide, and that makes the manganese the Mn2+, which is the form the plant takes up, and it becomes excessive and toxic to the corn. You see the healthy corn here that was growing in the lime soil area. So aluminum and manganese become toxic in strongly acid soils. How do we overcome acidity? We apply lime. Acidity in soils is a very weak acid. It's not strong sulfuric acid or strong hydrochloric acid. So you can apply a ton of lime per acre, and that amounts to 1 pound of lime per 1,000 pounds of soil. Not very much. It seems that way. A ton is about $58 now, but when you think 1 pound reduces the acidity in 1,000 pounds of soil, that's not very much lime to overcome that acidity. Forage responds very well to lime. This is crimson clover. It received 3 tons of lime in those plots. The plot next to it received none. You can see very few crimson clover plants, and they're nowhere growing like this. And this is alfalfa. This soil received no lime or boron. This soil was limed to pH 7 and received 4 pounds of boron. And we'll talk more about that in a little bit. So your plants respond to lime. Ryegrass, which many of us plant for winter pasture, at pH 6.2, it received 1.7 tons of lime, and it was disc incorporated into the soil, compared to no lime here, and the pH was 4.5. If you don't have a comparison like this in your pasture, and most of us don't, you look at this and think, well, I've got good ryegrass growing out there. I don't need to lime. But actually, that ryegrass is suffering from aluminum toxicity. It is not doing its growth to full capacity like this is, where the pH was 6.2, where it needed to be.
Isn't that 4.5 pH, isn't that pretty low?
Yes, that's extremely low. You don't ever want to let it get to 4.5 if you can help it. You want to sample your soils, test your soils frequently enough, like maybe every 2 or 3 years, to know when you need to get it limed to get it back up to about 6.2. Now let's talk a little bit of limestone quality and effectiveness. Quality actually begins at the quarry. In Texas, we're fortunate to have 2 quarries, one at Nolanville and one at Georgetown, that have 100% calcium carbonate lime. When that lime is blasted off the sidewall and they start to crush it, you can't change the calcium carbonate equivalent, so we abbreviate that CE. And then we have another term that describes how good the lime is, and that's the fineness of grind. When we combine CCE, calcium carbonate equivalents, and the fineness of grind, we come up with a term called effective calcium carbonate equivalence. Any lime particles that pass a 60 mesh screen, and that's 60 small, very small holes per linear inch in that screen. Any lime that passes a 60 mesh screen we consider 100% effective. So if you have 100% calcium carbonate in your lime and it all passes a 60 mesh screen, you have an ECC of about 100%. And that's what you want to apply. And we in Texas are fortunate that Texas crushed stone at Georgetown has a 99 to 100% ECCE lime. That's what you can get, like most of us are here from Lindale and somewhere north in Smith County. I don't want to mention any names, but a fertilizer company out of Lindale has 2 trucks, Killebrew trucks, running back and forth to Georgetown, bringing this high ECCE, very fine lime, to us up here. And Elhoist North America at Nolanville also has a 99 to 100% effective lime. It's even closer than Georgetown. Texas crushed stone historically sold a very coarse lime. And that's the material. When they crushed it and screened it, that's what they got. They've since started washing the fines off that coarse lime. They use the coarse materials for base material for cement pads for housing down near Georgetown and Austin. They make a lot more money off that now. And they take the fines that they get from that and they settle it in ponds, and they come up with a very fine 100% ECCE limestone. Other quarries that we have access to at Hugo and Idabel in Oklahoma, they have only coarse, low ECCE limestone. It's coarse enough that when I first started working on limestone fineness, one of the guys in the audience raised his hand and said, "Hey, you're right. There were 2 trucks spreading lime on my place, and the first truck knocked the windshield out of the second truck." Anyway, that's how coarse some of this can be. Mill Creek in Oklahoma, north of Tishomingo, has coarse and fine limestone, calcitic. They also have a fine dolomitic limestone. Dolomitic limestone has a much higher calcium content. So magnesium content. So if you need magnesium, you can apply a dolomitic limestone. Let's see how effective these different coarseness of limestone are. We took and applied an ECCE 62% and 100%, and then we mixed half and half and got an 81% ECCE limestone. We put out these limestone treatments at 1, 2, and 3 tons per acre, and 2.5 years later we planted crimson clover in those plots. Let's see how these coarse materials affected the yield. When we look at the very coarse material, it took 3 tons of that coarse material to optimize the yield of clover. When we looked at the half and half mixture, 81% ECCE, it took 2 tons of that material to neutralize the acidity to get the optimum crimson clover production. And guess what? You can guess what happened next. It took 1 ton of the ECCE 100 to do the same thing on crimson clover production. That's how good it is. The finer limestone is probably 3 times better than the coarse material, although that's not the way the lab recommends it. There's some people in this world, in the United States, Canada, and even internationally, that still think we need coarse particles in lime to hold the pH up in the soil once we lime it and get it up where we want it. Well, that's not true. The work we did, we applied lime in 1988, 91, and 92 at rates of 0, 1, and 2 tons per acre. So we've got 3 and 6 tons total applied lime. And then we looked at the pH 7 years after applying that lime with no more lime applied. And guess what? The finer lime, which raises the soil pH much higher initially than the coarse lime, was still holding the pH up well above that of the ECCE 62. That happened also at the 3-ton rate. But here's the kicker. 3 tons of the fine lime was holding the pH up nearly as high as 6 tons of the coarse lime. And the price difference between the coarse and the fine lime is only at the quarry. It may be $1 per ton different, $1 per ton more for the fine than for the coarse. The greatest cost is in the freight, getting it up here. So whenever you order lime, you have to tell them you want the superfine or ECCE 100% lime. Now let's get away from lime just for a minute. When we talk about fertilizers in a blend or in a bag, what are we actually talking about? You see a bag of fertilizer that says 10, 20, 10 across the bag. When we look at that, we're actually looking at the nitrogen, phosphate, and potash in that bag, and if there's anything beyond that, they list it as sulfur, and that's shown down here at 6%. That first number is nitrogen, second number is phosphate, and the third number is potash. That's in the bag or in blends. You don't get to see it in the blends, but that's what it is. I was hoping that Charles Lane with Lane Fertilizer would be here, and I invited him, but he said he probably couldn't. He didn't want to come and argue with me tonight. We compared urea ammonium nitrate. Remember, that's the liquid with urea and with ammonium nitrate and ammonium sulfate. I look at ammonium nitrate as a standard. As to me, that's the best nitrogen fertilizer there is because it doesn't lose ammonia through volatilization when you apply it and leave it on the soil surface. It might lose about 2% is the maximum, whereas urea and UAN can lose quite a bit more than that. Anyway, we have compared those nitrogen sources at 40, 80, and 120 pounds of nitrogen per acre per each application, and we applied 3 applications in year 1, 4 in year 2, and 5 in year 3. And we were trying to apply this nitrogen at a time when it wasn't going to rain to give it an optimum time to do its volatilization. So at the 40-pound N rate, we're looking at 20% less yield from UAN than from ammonium nitrate. When urea was compared to ammonium nitrate at 40 pounds of N per acre, we got a 14% lower yield than we did with ammonium nitrate. However, as we increase the rate of nitrogen, the differences become less. Ammonium sulfate at 40 and 80 was equal to ammonium nitrate. But when we went up to 120 pounds per application, and that's a lot of nitrogen over 3 years, the differences kind of evened out because we were applying excess nitrogen beyond what the plants needed to grow. So the differences weren't that great at the high rates of nitrogen. But look at the ammonium sulfate. It started to lose production compared to ammonium nitrate when we went to those high rates because we were acidifying the soil. And aluminum was starting to come into play where it may have been toxic to plant growth. Phosphorus, very important. If your soil tests very low in phosphorus, you want to get all the phosphorus applied in the spring. Don't divide it up in different applications with nitrogen throughout the season. Otherwise, your plants are going to be deficient on phosphorus throughout the growing season. But if your soil test is medium and you want to put out a little bit of phosphorus to maintain the phosphorus level in the soil, then you can apply a little bit of phosphorus with each application of nitrogen. Phosphorus is important in increasing root growth, reproduction, and energy transfer and storage in the plant. Plants take up phosphorus as orthophosphate, not as P2O5 as shown in on the fertilizer bag. This clover was growing where we applied 80 pounds of phosphorus compared to no phosphorus, and the phosphorus level in this soil was 3 parts per million, extremely low. That's why the clover wasn't doing much here. Potassium is another important nutrient for plants. In this study, we applied from 0 to 402 pounds of potassium, and we split those applications into 3. And then we compared those at 80 pounds of nitrogen or 160 pounds of nitrogen per application. That 160 is way, way up there. You don't ever want to apply that much at one time. When we look at the response of Tifton 85 Bermuda grass to potassium at the 80-pound nitrogen rate, the blue bars, we've optimized yield with only 134 or so pounds of potash rather. When we increased the nitrogen rate to 160 per application, we started to see a much greater increase in response to potassium. And my recommendation for potassium is you want to apply the same amount of potassium as you put out nitrogen each time on these hybrid Bermuda grasses. So if you put out 100 pounds of nitrogen, put out 100 pounds of potash. In Georgia, they're recommending a 4:1:5 ratio of nitrogen to phosphorus and potassium. They're recommending more potassium than they are nitrogen. And I can't argue with that. I think it's that important.
So is that the same for all types of soils, such as sand?
It's the same for hybrid Bermuda grasses, like Tifton 85 and coastal.
Even though your soil sample may show much higher in potassium than it does nitrogen?
Usually, yes, but in our soils, potassium is usually always deficient. Potassium is important in root growth. Root growth and rhizome are the same terminology for Bermuda grass. This study was done before my time at Overton. They kept nitrogen and phosphorus rates the same across, and they increased the potassium from 0 to 240. And at the higher potassium rate, they produced about 1,400 pounds more rhizomes in the soil than when they didn't apply any potassium. And look how poor those roots look. They look rotten compared to the nice white roots over here. Just a little bit about micronutrients. I have not found response of clovers or Bermuda grass to micronutrients other than finding clovers responding to boron on limed acid soils. In alkaline soils down near Beeville, clovers responded to iron. And that's about all I can say on the micronutrients, except with alfalfa. When we had no lime and no boron, we got no alfalfa. When we applied lime to get the pH up to 7 and 4 pounds of boron, we actually produced 2 tons more alfalfa dry matter from 4 pounds of boron. That may be about a $35, $40 investment to get 2 tons of alfalfa that you could sell for maybe $10, $12 a small square bale, and there would be 27 small square bales in a ton. 4 pounds of boron makes a lot of difference in that regard. Now, how much fertilizer is needed for forage production? That depends on what forage you're producing, the anticipated yield, how much rainfall you think you're going to get, or if you've got the potential to irrigate it, and the nutrient content of the soil. To learn the nutrient content of your soil, you do that by collecting a soil sample and having it analyzed by the lab. And now we're going to get to the topic I was supposed to talk about tonight. Before we do, I want you to understand something here. This is pH over time, 3 years. The dips are fall. The highs are in the spring. And if you're going to sample your soil, you always want to sample it at the same time of the year, because you will avoid seeing about a 1 point pH change, 1.0 pH change from spring to fall. So if you're going to sample in the fall. That's my recommendation. Or if you're going to have to sample in the spring, always sample in the spring to make sure this is constant. And I want to indicate here that soils are not uniform, so it's very important to take a sufficient number of subsamples to represent your field. The more you take, the better representation you can get. Here we did a 50-foot quadrant across this 12 or so acre fescue field that was always treated as one unit. And we sampled the soil at the intersecting points of that quadrant, north, south, and east and west, where those lines crossed. And we ran pH on those samples. And that field was a mess. We had highs up to about 6.2 and lows down to about 4.2 across that field. So you've got to take a sufficient number of samples to try to get a good representation of that field. Sampling equipment on what I want to do, you can use a shovel, but it's a lot harder than using this equipment. And you want to have a clean plastic bucket. I don't use these very much anymore because I found a better way. I can get on my four-wheeler with a portable electric drill and a drill bit that we use to drill holes in wood, and I can go drive around that field randomly, lean over, put that drill bit down on the soil, turn it on, drill it down to 6 inches, pull it out, and if the soil is moist, the soil stays on that bit. I put it in a bucket, spin the bit, and it flies off into the bucket. Saves a lot of walking. However, if the soil is dry, it's going to fall off that bit. So here's an answer. You drill a hole through a plastic bucket, and you put the bit down into the soil through that hole. When you draw the bit back out, the soil comes into the bucket. Excuse me. And when you get the soil in that bucket around the hole, you tilt the bucket to get the soil to the side of it. However, with this method, when you sample in dry soil, you've got to get on and off that four-wheeler. is not as easy as if you sample when the soil is moist. What are the steps involved in getting your soil tested? First, you need to get soil sample bags and information forms. Usually you can get these from your county agent. However, you can Google the laboratory like Texas A&M at College Station Soil Testing Lab, and they will have a printable form that you can print right there at home. You don't have to go to the county agent's office. And you don't need to use their soil sample bags. You can use Ziploc plastic bags just as well.
Dr. Haby.
Yes, sir.
Smith County Soil and Water Conservation District is break it into the NRA cost.
It will cost you about $3 a sample through the Soil and Water Conservation Board. So they'll do 2 samples per producer per year at a cost of about $3 instead of 10 or 12, whatever the labs charge. How do you access that, James?
Through the NRC office.
Oh, go through the NRCS office to get that done.
Here in Tyler.
In Tyler.
Where's that at?
When you get your soil sample bags and your bucket and the method you're going to use to pull the samples, you want to...
Take care of the postage, too.
Pardon?
We'll take care of the postage, too.
They'll take care of the postage on those also to mail them. When you get your bags and everything ready, you go out and collect your samples into the bucket, and you want to take 15 to 20 subsamples per a 15, 20 acre field. In other words, about 1 subsample per acre, roughly. You want to thoroughly mix those subsamples in the bucket and take about a pound of soil out as a composite. Put it in your container, bag, whatever you're going to put it into. Take it to your shop and get it air dry if you can. I usually do that with a light breeze from a fan blowing over these soil samples. I'll explain why in a little bit. Write your name and address on the sample and the sample ID on the bag. And then you want to complete the information form. You want to put your name, address, the sample numbers, the test desired, the crop to be grown, whatever the sample information form calls for. You want to write that down to give them at the lab some idea of what they are doing. Then box up and mail the samples and information forms. And in Texas, we have 2 public labs, Soil, Water, and Forage Testing Laboratory at College Station, or you can send the samples to Stephen F. Austin. They have a plant soil and water analysis laboratory. It's your choice. Or you can send them to a commercial lab. Once the samples are analyzed, you'll get a report back from the lab. And in this case, this came from the Extension Laboratory in College Station. They analyzed this soil for pH, conductivity. Conductivity is a measure of the salt content, the electrical conductance due to salt content in that soil. They determined nitrate, nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, and sodium. They gave a printout of the results, and they showed it as parts per million. pH has no units, and conductivity is a term you don't understand, and I hardly do myself. They also use a bar graph to show the concentration of those nutrients in that soil, and then they give a fertilizer recommendation over on the right. So all you need to do when you get your test results back is call your fertilizer dealer and say, the lab recommended so-and-so per acre. Give them this information right here, or take it to them in person if you want, and they will mix up a blend to put in their trucks and bring out to your place and apply it.
May I make a comment?
Yes, sir.
Now, what they recommend, kind of take with a grain of salt. Because if you look at it and it's dry, and the weather forecast says it's going to be fairly dry, you don't want to go out there and put 400 pounds of, just say 21, 6, 12 on there. You want to back off, because you'll burn it pretty bad if it stays dry.
I don't necessarily agree with what you said, James, because you're going to get it out there. The soil is dry. When it rains, you want it out there. You don't want to put it out after the rain and hope you're going to get it into the soil. I have not seen forage burn, as you call it. By burn, I'm thinking you're going to dry out the plants. I have never seen that. And I put out a lot of nitrogen, a lot of material at very high rates in small plots. I don't agree that you can burn unless you put out bukus of fertilizer. You're not going to burn that grass.
It don't seem like I get the yield when you get it. All you get on that application of fertilizer is an inch for the rain. You just don't.
What nitrogen source are you using?
At that time, I was using urea.
Okay, you were using urea. You put it out there and it lays there on the dry soil. You think it's laying on dry soil, but dew and humidity will cause that urea to react and volatilize and lose nitrogen. Ammonium nitrate won't do that. You can put that out. You can wait a month or two. When rain comes, you're going to get the results from that one. It does not lose nitrogen as ammonia volatilization, maybe 2% compared to urea on corn across the nation. I've seen results where urea lost 40% of its nitrogen due to volatilization. That's significant. Now I'm done. If you have any questions, feel free. This is the time to ask them. And one other thing, you can look for your pot of gold at the website overton.tamu.edu. Once you get on that website, click on pastures, forage, beef, and horticulture, and you'll get about 195 key words. Almost anything you want to learn about will be on that website in very short, concise reports, like about 2 or 3 pages. I hope that you'll access it. Yes, sir.
I've always been told, seen, and known, when I see pastures that look like they're run down, they got a lot of broom sedge out there. I've always said, you bad need some lime on it when you see broom sedge grow up on it.
When you see broom sedge, what do they call that? Wheatgrass also, something like that?
I always call it broom sedge.
It's because you have a very acid soil and it lacks phosphorus. Very poor soil.
It's been neglected for years and nothing's been
Yes.
nothing's ever been done, but that broom sedge will be up that tall.
You're right. I've got a neighbor that has that situation, and he is now soil testing to see what he needs on that field.
I've seen them cut it and bale it and say it's better than a snowball, but that's
That's probably right. Anything else? Anybody? Now's your chance.
So, I've got pure sand, and there's some low areas that nothing grows but grassburr, some other weeds. The Bermuda won't grow. And when I've taken separate soil samples from there, pretty much shows the same thing as far as nutrients as the other areas. Is there something else going on?
That's a hard one to explain. You need to put something on like Prowl H2O to take care of that. That's a tough one. I only have spots of sand burr on our place, and I don't know how it got there, but when I find these spots, I take what they call a pear burner in southwest Texas to burn thorns off cactus for cows to eat when they don't have anything else in a drought. And I send those sand burrs to hell.
So what,
They've got some company from my place.
I don't know what you do about them except try to control them chemically. And
if I control them chemically, almost nothing grows there. The Bermuda won't grow. The coastal won't grow.
and you don't get enough rain to keep that sand moist to get the lime and the fertilizer to work.
Much lower elevation than right beside it, and that grows pretty good when I fertilize it.
Okay.
Down that bottom, it won't grow anything. I asked Lane one time, he just said there's too much sand. But I mean, the whole place is pure sand.
Okay, you have a new county agent here in Smith County. Get him out there and let him do some research on chemicals. He is an expert on chemicals. He used to work for a chemical company. I'm sure he would like to do some demonstration work on that site.
Who is that?
There you go.
Who is that?
Clint Perkins.
He was leaving as we came in.
That's all I have, folks. If any other questions, you can see me afterwards.
I brought the sample, there's information sheets and soil sample bags up front there for anybody who would like to have them to send your soil samples in.
Thank you.